Welcome back to another math video here at Math Rocks with Mr. Cox. This video is going to be centered on figures, and in particular something called similar figures. So as you can see here, we have figure 1 and we have figure 2, and just from an English point of view, they look kind of similar. But in math, it means something a little bit different. We have to be able to look at these figures, and there's going to be some identifying characteristics that make one figure similar to another, having to do with the angles and the sides. Also in this video, we're going to be looking at how to prove that two triangles are similar. So stick around and let's get it on! The first thing we're going to do is we're going to look at what actually makes figures similar. So I've got a figure here on the left and a figure here on the right, and up here it says ABCD, that figure is similar to EFGH. So what makes them to actually be similar is this. They're similar if the corresponding sides are what we call proportional, more on that in a moment, and all the corresponding angles are actually congruent. Well, the angles are fairly obvious here. On the bottom, we have a right angle and a right angle. Same thing over here at angle E and F. We have a 72 degrees here, 108 here, 72 degrees, 108. So clearly the angles are congruent. So proportional merely means this. If you were to take, for instance, this side up here, CD, the side that corresponds to that, you'll notice here CD are the last two letters in ABCD. The last two letters over here are GH. If I locate GH right over here, you'll notice that if you were to take 9 and multiply it by 2, that would make it 18. If you take another set of sides, for instance, let's take 7 down here. Those are the first two letters, A, B, of this one here. The first two letters here are E, F. And you'll notice that 7 times 2 equals 14. It looks like, if we look at the figure on the left, if we double the side lengths, it would equal the length of the ones on the right. And it holds true for all of them. In other words, if we took 18 over 9, which is the first one, or we took 14 over 7, or we took any of the other ones. For instance, if we took 6, and its corresponding side would be over here, 6 over 3, and then our final one would be 16 and 8, every single time that proportion would be a 2-to-1 ratio here. So that's what we mean by proportional. Let's go ahead now and put it into use, and we have two similar figures here. This time we have pentagons, A, B, C, D, E, and then J, K, L, M, N, and they are similar. So we're going to find some missing sides here. So I'm going to look at, A, B, the first two letters here, and that's X. And I'm going to look at the side on the other figure, J, K. So J, K, where is that? It's over here. So you have to be a little careful here and not just assume, well, it's the side kind of on the left-hand side here. We're going to start with like NJ. No, we have to look at the letter scheme here. So the first two letters is AB. Therefore, we're looking at the side of the first two letters here, which is JK. So X and 20 are going to kind of go together. BC would be the next two letters. So that would be 4, and that would be equivocal to KL. Those would correspond. That would be over here. So now we can go ahead and actually solve for this. We can say, for instance, I'm going to start with the bigger numbers here. I'm going to say 20 is to X as a proportion. 20 is to X should be equivalent to 10 over 4. And from here, all we have to do is cross multiply. 10 times X would be 10X. And then 20 times 4 would be 80. And then if we go ahead and divide both sides by 10, we would get 80 divided by 10 is 8. So now we know what X is. Next up, let's keep going here. So CD would be the third and the fourth letter. The third and the fourth letter in the other one would be L and M. So CD would be Y, and LM would be over here. So we can use 15 and Y. They would correspond to each other. So I'm going to use the 10 and the 4 again. So here's my 10 is to 4. So if I say 10 is to 4, I need to say 15 over Y. And once again, I have proportions that I can solve. So 10 times y is 10y. 4 times 15 is 60. And if I divide both sides by 10, I get y equals 6. And let's see here. Finally here, we have, let's see here. We have z. Notice how we have a missing side over here. So I'm just going to find the one side we know for sure is Z, although we don't know the value yet, but at least we know it's Z. MN. So MN are the last two letters here. So I'm going to look for the last two letters here, DE. So that means it's going to go with 10. 9, although it's in our figure, is not going to really be useful at all because JN, we actually have no value over there. So we're going to go ahead and again look at the 10 and the 4 because those are where we have numbers in both figures. So I'm going to say 10 is to 4, and because I'm trying to find Z right now, I'm going to say Z over 10. Once you've done that, you can cross multiply. 4 times Z is 4Z. 10 times 10 would be 100. And now if we divide by 4, Z would end up being 25. So really the tricky thing in these is finding out which sides correspond with each other. And if you look at the letters and how they're arranged here, that's the easiest way to do it. Sometimes the drawings can be a little tricky. If you like what you've seen and heard so far, please like, comment, or subscribe. Thank you, and back to part 2. We're going to go ahead right now and look at how we prove that triangles are similar. And as in congruent triangles, there are some shortcuts to prove that triangles are indeed similar. There's 3 of them. So one of them is called side, 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 and that's SSS similarity here. And rather than being congruent, what it means again is that the sides are actually proportional. So if I were to go ahead now and look at the smallest side, that's a 3, and over here the smallest side is a 6, you will notice that if I take any other sides, like for instance the biggest side here is a 7, and that's a 14, that every single time if I were to take 6 over 3, or if I take the biggest side and over the biggest side here, 14 over 7, and then same thing here for the middle sides, 10 and 5, my ratios or my proportions are consistently always 2. 6 over 3, 14 over 7, or 10 over 5. The second type is called SAS, very comparable to the one you just saw. The only difference is we don't have all the sides, but we have 2 sides, and the ratios would be the same. We could have 24 over 8, that would be 3, 30 over 10 would also be 3, and then the angle in between them needs to be congruent, and they're both 33 degrees. And the final one would be angle, angle, and that's where we have 2 angles that are congruent. We don't really need to say the third one because we all know that when you have a triangle, the sum of all the angles is 180 degrees. That is the triangle angle sum theorem. So once we know that 2 of them are congruent to each other, we definitely know that the third is as well. So those are your 3 shortcuts to prove that triangles are similar. Let's go ahead now and actually use a flow chart to prove that these triangles are similar. So clearly in the picture, I hope you all can see there's a little small triangle right here. And there's also a bigger one. So the smaller one, I could call that triangle PAE. So I'm going to go ahead and write that down here as our final step, triangle PAE. And we're going to prove that it's similar to the other bigger triangle, which would be triangle PST. And we'll worry about the reason why later. Also, I think we can all see that this is 15 in length and this side is 21 units. Let's go ahead and draw the bigger one, and so maybe it's a little bit easier to see what those side lengths are. So that's P to S to T. So here's my P, here's my S, here's my T. From P to S would be 15 plus 10, or 25, and 21 plus 14 would be 35. So let's start the process now of actually using some given information. So I'm going to go ahead and write given here. And then first let's address the sides to see if the proportions are the same. So I'm going to look at the bigger triangle here. So if I look at PT, that distance, so in math we would write just PT, that distance is 35. And this other distance, the side that corresponds with it, would be PE. And PE has a length of 21. If I divide these both by 7, 7 goes in there 5 times, and 7 goes in there 3 times. So that's my ratio of the sides. It's a 5 to 3 ratio here of the bigger to the smaller. And let's go ahead and look at the other given bit of information here, and that would be the smaller sides. So I'm going to use PS, and its side length from P to S is 25, and then it corresponds with PA. And PA would be a distance of 15. I'm going to go ahead and reduce this fraction. 5 goes into both of them. So 5 goes in here 5 times. 5 goes into 15 three times. So indeed, you'll see that my ratios are the same, 5 over 3. So the sides are definitely proportional. That's all the given information we're given. So we're going to have to look a little deeper here to find something else. I do notice, though, that they have angle P is in both of them. Okay, they kind of share that angle as part of each figure. So you can literally say now angle P is congruent to angle P since they share that angle. Now what we're going to write as a reason is called a reflexive property. So the reflexive property works when you have sides that are shared by the two figures or triangles, and in this case we can also use it if they share an angle. So which of the three ones is it? Well, we have two sides in the angle in between them, so it's going to be side, angle, side, similarity. So that's how you prove that triangles are similar. I hope you've gotten a lot out of this video, and I hope to see you again soon. Thanks for watching.